Section: Introduction. We, in our paper, explore how large language models, which have already shown impressive abilities by learning from vast amounts of text data, can further enhance their performance through reinforcement learning from human feedback, RLHF, even with relatively few interactions. The increasing use of chatbots presents a unique opportunity to collect more human feedback, which could lead to the development of new capabilities, possibly even superhuman ingenuity. This raises an interesting question. If these models only learn from humans, how can they achieve beyond human-level creativity? We suggest that this might be possible because it's easier to rate the quality of an idea than to come up with one. For instance, if a model generates a huge number of ideas, human feedback can help identify the truly ingenious ones, which can then be built upon to push the boundaries of creativity further. In our study, we highlight the significant advantages of actively seeking out feedback to improve model performance more efficiently, potentially speeding up the achievement of superhuman creativity by years or even decades. Typically, in RLHF, queries consisting of a prompt and 2 different responses are sent to human raters, who then indicate their preference. This feedback is used to adjust the model's responses to better align with human preferences. We focus on this type of interaction but introduce the concept of active exploration, where the model seeks feedback in a more targeted way, as opposed to passive exploration, which relies on randomly generated responses. We compare several active exploration strategies, including Boltzmann exploration, which favors responses predicted to be more rewarding, and 2 methods that utilize uncertainty estimates from an epistemic neural network, ENN, Infomax, which aims to maximize the information gained from feedback, and double Thompson sampling, which chooses responses based on their likelihood of being the best option. Our findings, illustrated through experiments, show that active exploration, particularly using double Thompson sampling, significantly reduces the number of queries needed to achieve high performance levels. Our experimentation pipeline involves 2 main parts: a learning pipeline, where the model learns from sequential feedback on queries, and an assessment pipeline, where the model's performance is evaluated against a baseline. Each query consists of a prompt and 2 responses, with the model generating multiple candidate responses and selecting 2 based on its exploration strategy. The feedback is simulated based on human preferences, using a reward model trained on previous queries and responses. This setup allows us to compare the effectiveness of different exploration strategies without the computational burden of policy gradient methods, which are commonly used but can be complex and opaque. In summary, our work demonstrates the potential of active exploration in enhancing the performance of large language models through reinforcement learning from human feedback, offering a promising avenue toward achieving superhuman creativity more quickly. Section Summary. The section introduces the concept of reinforcement learning from human feedback, RLHF, to enhance the capabilities of large language models. It discusses the potential for gathering increasing volumes of human feedback through chatbot interactions, leading to the emergence of superhuman ingenuity in content generation. The section also presents evidence of significant benefits from active exploration in tuning large language models, demonstrating that high levels of performance can be achieved with far less feedback, potentially accelerating the attainment of superhuman ingenuity by decades. Section: Reward Model Architectures and Training. We explore different ways to guide how responses are chosen, both when learning and when evaluating our experiments. We look at 2 kinds of models that predict rewards based on the data we've seen. The first model gives a straightforward reward for each combination of a prompt and its response. The second model adds a bit of randomness to the reward prediction, which helps us account for what we don't know or are unsure about. Let's talk about how we set up and train these models. We use a special kind of neural network that takes in the output of the Gemini Nano language model. This output is essentially a complex representation of the text we feed into it. To decide on a reward for a prompt-response pair, we first process it with the language model and then with our reward predicting model. For the first type of model, we use a simple network known as a multilayer perceptron, MLP. This network takes the complex text representation and outputs a single number as the reward. We adjust the model based on comparisons between pairs of responses to a prompt, where we know which response is preferred. We use a specific formula to make these adjustments, aiming to minimize errors in prediction while also keeping the model simple. For the second type, we use what's called an epistemic neural network, ENN, to handle uncertainty in our reward predictions. This model is a bit more complex because it considers a range of possible scenarios when predicting rewards. We adjust this model by a similar process, but we also include a step that accounts for different levels of uncertainty. To train these models, we collect data from interactions and store it. Then, we use a method called stochastic gradient descent, tweaking the models bit by bit to improve their predictions. This process involves taking small samples from our collected data and making adjustments based on those samples. We also explore different ways to choose which responses to evaluate. One method is passive exploration, where responses are chosen randomly. Another method, which we call active exploration, uses the reward model to pick responses that are likely to be informative based on past feedback. This can help us learn more efficiently. In our experiments, we found that active exploration, particularly using a method called Boltzmann exploration, works well. This method picks responses based on how likely they are to be useful, according to the reward model. It can adjust how adventurous it is in exploring different responses, which can be fine-tuned with a parameter we call temperature. In summary, we've developed and tested different models and methods for predicting rewards and choosing responses in a way that helps us learn effectively from feedback. Our findings suggest that using these models, especially with active exploration strategies, can significantly improve the learning process. Section Summary. The section discusses the use of reward models in guiding response selection and describes two types of reward models: point estimate and epistemic neural networks, ENNs. The point estimate reward model is a feed-forward multi-layer perceptron trained on preference data, while the ENN models epistemic uncertainty about reward by sampling an epistemic index from a reference distribution. The training process involves maintaining a replay buffer and applying stochastic gradient descent, SGD, with respect to the loss functions. Additionally, the section introduces exploration algorithms, including passive exploration and Boltzmann exploration, which utilizes the trained reward model for active exploration by tailoring responses based on past feedback to gather more useful future feedback. Section: Active exploration with an ENN. We're now going to talk about how we use a special kind of reward model called an ENN, or epistemic neural network, to explore different options actively. Imagine you're trying to figure out how good different responses are to certain prompts, but there's a twist. The value you assign to each response doesn't just depend on the prompt and response itself, but also on something we call an epistemic index. This index helps us measure how uncertain we are about the reward. By looking at how this uncertainty changes when we consider different indices, we can get a better idea of what we don't know. One method we use with the ENN is called Infomax. It starts by creating a bunch of responses, then it looks at a bunch of these epistemic indices. For each pair of responses, the ENN tries to guess which one a human would prefer, and Infomax looks at how uncertain these guesses are. The goal is to pick the pair of responses that leaves us the most uncertain, because figuring out which of these is better could teach us a lot. However, Infomax isn't perfect. Sometimes it spends too much effort learning about responses that we already know aren't very good. That's where double Thompson sampling, or double TS, comes in. It's a bit smarter about choosing which responses to compare, aiming to pick ones that both have a shot at being the best. In our experiments, we tested these methods by having agents generate responses to prompts and then seeing which responses were preferred. Each agent worked with 32 prompts at a time, and for each prompt, it generated a pair of responses. We kept track of the feedback for these pairs in something called a replay buffer, which is just a fancy way of storing recent data. We compared the agent's choices to those of a standard model we call Gemini Nano, using a bunch of test prompts to see which agent picked the best responses. To make these decisions, the agents used a network of multiple smaller networks, or MLPs, each making its own predictions. We also played around with the settings for our exploration methods, like how many indices to consider or how many tries to give for getting a distinct second response. In summary, we're using these advanced methods to better understand how to choose the best responses to prompts by embracing uncertainty and learning from it. This approach helps us refine our models and make smarter decisions about which responses are likely to be the most helpful or preferred. Section Summary. The section discusses the use of an epistemic neural network, ENN, reward model in exploration algorithms. Infomax algorithm uses the ENN reward model to maximize uncertainty in human preference, while double Thompson sampling focuses on selecting responses with a chance of being optimal. The experiments involve interaction epochs, updating reward models, and assessing performance based on win rates relative to Gemini Nano on out-of-sample prompts. Section: Assessment of exploration algorithms. We evaluated different algorithms to see how well they can learn and improve their performance over time. By looking at the win rates of each agent across various epochs or periods of interaction, we found that agents that actively explore tend to learn faster and win more often. Among these, the double Thompson sampling (TS) agent stood out as the best performer. We noticed that the Infomax algorithm started strong in the early stages but couldn't keep up with double TS as time went on. This might be because Infomax focuses too much on gathering information, without considering if that information will lead to better outcomes. Although all the agents seemed to improve at first, their performance plateaued after a while. This plateau is likely due to the limits of the reward model's capacity, which is akin to how much it can learn from feedback. We expected this leveling off because, with enough data, any model will reach its learning limit. However, increasing the model's capacity could allow for continued improvement, albeit at the cost of more computing power. This ties into the idea that it's useful to adjust the complexity of what an agent is trying to learn based on how long it will be exploring. When we looked at how much data was needed for other algorithms to match double TS's performance, we found that the benefits of efficient exploration become more significant as the amount of feedback data increases. For example, to achieve what double TS could with 30,000 pieces of feedback, other methods might need 10 times more data. This suggests that with enough data, efficient exploration could drastically speed up learning, potentially leading to breakthroughs in creativity much sooner than expected. In terms of selecting which queries to explore, Boltzmann exploration did the best among the methods that rely on a fixed reward model. However, double TS's success is largely due to its use of uncertainty estimates from our enhanced neural network, ENN, reward model. We compared the uncertainty estimates of our models and found that the ENN model provided much more reliable uncertainty estimates, which helped in making better decisions. To get a clearer picture of how double TS outperforms other methods, we looked at how it evaluates responses to a specific prompt compared to Boltzmann exploration. We focused on one prompt and two possible responses, observing how the model's preferences evolved with more data. Initially, both models were uncertain, but as they learned from more feedback, double TS consistently showed a preference for the more popular response, as indicated by human feedback. Boltzmann exploration, lacking uncertainty guidance, stuck with the less preferred response. This demonstrates the value of incorporating uncertainty into decision-making, allowing double TS to adjust its strategy and ultimately make better choices. Section Summary. The assessment of exploration algorithms shows that actively exploring accelerates learning and leads to higher win rates, with the double TS agent emerging as the top performer. Increasing the capacity of the reward model enables further improvement at the cost of increased computation, and efficient exploration may offer a multiplier effect reaching several orders of magnitude as the number of interactions grows. Additionally, the quality of uncertainty estimates offered by the ENN reward model plays a crucial role in the performance of exploration algorithms, as demonstrated by the large improvement enabled by uncertainty estimates in the double TS algorithm. Section: Closing remarks. We believe that the findings we've shared are the first to show significant advantages of actively exploring when fine-tuning large language models. However, there's still a lot of potential for further investigation in this field. To wrap up our paper, we want to highlight some key areas for future research. In our experiments, we used a very basic version of an ensemble neural network, ENN, architecture, which consists of multiple multi-layer perceptrons, MLPs, working together. While this setup has its merits, other architectures have been found to balance the computational demands and the accuracy of uncertainty estimates more effectively. As we gather more feedback data from humans, it might be beneficial to design ENNs based on transformer models instead of MLPs to enhance performance. Another aspect we noticed is that our reward model architectures only modify the head of the language model, which processes the final layer's output. We could potentially see better results by also adjusting the torso of the language model, not just the head. Although efficient exploration has its benefits, figuring out the best ways to explore while adjusting more parts of the language model is something we need to look into further. Lastly, exploring multi-turn dialogues presents a fascinating and crucial area for future research. In our study, we looked at exploration as a way to quickly find a single response that seems appropriate. However, in multi-turn dialogues, the goal might shift towards selecting responses that better shape the flow of the conversation. The concept of deep exploration, which involves finding effective responses that contribute to a sequence of interactions, is challenging but could significantly improve dialogue systems. In summary, while we've made some promising strides in using active exploration to fine-tune large language models, there's a wealth of opportunities for deeper investigation and improvement, especially in the realms of ENN architecture, model tuning, and multi-turn dialogue exploration.